Hello everyone, welcome back to Deterministic Optimization. Let's continue our discussion on radiation therapy planning. So the learning objective for this lesson is we'll create linear programming models for radiation therapy planning. We'll first create an idealistic LP model. We'll see exactly why I call it idealistic. And then I'll create a realistic model for radiation therapy planning, but unfortunately the model becomes nonlinear programming. But lucky thing is we can reformulate as a linear programming using the techniques that we have learned in the previous lecture. Okay, the radiation therapy planning problem is the following. Given a tumor area, that is the red area here, and given a critical area, that's the blue area, given a set of possible beamlet origins, this is determined by the machine itself, and angles. We assume the angles of this beamlet are also fixed. In a more complicated optimization problem, the angle may actually change. That could also be an optimization variable, but here we consider them as fixed. The optimization problem for us is to determine how much radiation each beamlet should radiate, or in other words, the weight of each beamlet, so that the total dose over the tumor area will meet a certain target level, and the total dose over the critical area cannot be too high, cannot be more than a certain target level. So this is the radiation therapy planning problem. In order to solve this, we first need to discretize the radiation area. Similar to the decision-making under uncertainty problem, we have random variable, we need to first discretize it. So it's here, we have a continuous area of tumor and critical area. In order to make decision, we need to discretize this radiation area by grid. So each little grid here is called a pixel, and it's represented by its coordinates x and y. So we partitioned the radiation area into a 2D pixel in this case. In practice, you may need a 3D structure, and then each pixel is called a voxel in a 3D case. So we also need beamlet data. So what is beamlet data? Beamlet data specifies the unit dose delivered quantity for each beamlet, meaning the unit amount of radiation that each beamlet can deliver. So here is the way that we represent the beamlet data. So this is a matrix that represents the x and y's of the pixels in the discretized region. And if the beamlet is coming in this direction, that angle is fixed. So this direction is known, and once the beamlet comes in this direction, the radiation dose will also be determined beforehand. This is by the unit amount of dose. For example, the dose at this pixel is 1, and then it decays. So all these numbers are from manufacturing, specification, or measurement. These are known for the unit amount of dose. Some other area that's not radiated by this beam will be 0. So this is a data matrix or a beamlet matrix for one beamlet that coming in this area, this direction. So, and more specifically, for beamlet P, that data is a matrix. So each pixel x, I, and j has a certain number. So dpij is the number, for example, 0.7, 0, and everything here. And then d of p is that matrix, is this matrix here for each beamlet. And beamlets can come in from different angle and may have different unit dose strength. So this data matrix is different for each beamlet. Okay, we'll use this data to formulate a linear optimization model first. The decision variable is the weight of how much units of delivered dose that we want from each beamlet. There's a unit of delivery, and W1 means how many units of the delivery. we want for beamlet 1 up to beamlet n. Suppose there are n unit beamlets. The objective is to minimize the total beamlet radiation over the entire area. So we have tumor area denoted by T. This is a set of pixels for tumors. And C is the set of pixels for the critical area. N is the set of pixels for normal area. And the union is the total. That's the set of all pixels. So we want to minimize the total radiation level, summing over all the pixels, because radiation is bad for normal tissues. We want to minimize that. And each Dij is the dose, the total dose received by pixel ij, and that is the sum over all the beamlets from 1 to big N, that the total number of beamlets we have. And each beamlet has a unit amount of dose delivery from beamlet P to pixel ij, and multiply by how many units of dose that we determine to use beamlet P to deliver. So this sum is Dij. That's the cumulated dose received by pixel ij, and we want to calculate this for every pixel in this entire area. And the weight of each beamlet should be non-negative, and each Dij, the dose received by pixel ij, should be greater than or equal to a lower level if the pixel is a tumor area, or if the pixel is a critical area, then it should not be more than a certain target level. So this is a linear programming model. But unfortunately, this linear programming model looks very simple. The problem is this model is usually infeasible. Because of the complicated shape of the tumor, it's usually impossible to get a radiation plan so that the tumor area get enough radiation and the critical area get not much radiation, because this kind of shape. So this linear programming model is simple, but it's idealistic model. It's not realistic in a real situation if the tumor has very complicated shape. So what do? We want to build a realistic nonlinear optimization model. And the way to do that is the following. There are many different ways, and we'll see one way, and we give actually two models. So we can set a target level of dose for each pixel ij. This can be determined by the physician to say at each pixel, the pixel, depending on its either a tumor or a critical area or normal area, the physician will say this is the target level of dose at that pixel. And we require the optimization problem to come up with a delivery plan so that the delivered dose is as close as possible to that target level. So you see that as close as possible is measured by certain distance. So again, we'll minimize a distance from the planned deliver to the target deliver. So how do we measure that distance? So here is one way. We use the L1 metric to measure the total absolute difference between the realized delivered dose and the target delivered dose. So that's how we measure the minimum of the sum, the total sum over each pixel of the difference, the absolute value of the difference between the realized dose from radiation and the targeted dose. And each Dij, again, is the sum over all the beamlets delivered to the pixel ij. And we have a weight, non-negative. So this is an optimization problem, and it's always feasible because any non-negative W you put in will be a feasible solution here. So there is no feasibility problem here. And we want to have the total delivered dose as close as possible to the target measured in this distance function. Here's another way to measure the distance. The distance is measured as the maximum difference, absolute value difference between the realized dose and the target dose. So we want to minimize the maximum error. Whereas in the first case, essentially we're minimizing the total error or equivalently the average error. So this second metric is called L infinity metric. The name doesn't matter, but here we have a minimization of a maximum. So both problems are nonlinear. How do we reformulate as a linear programming model? So we can use the same trick that we learned in the previous lecture. For the L1 metric, minimize the total absolute value difference. We can use the same trick, introduce a new variable, Zij, that is greater than or equal to this absolute value for each pixel ij, and then reformulate that constraint as the inside of the absolute value should be less than or equal to Zij and greater than or equal to negative Zij. This is a linear constraint, and we have all the other remaining constraints. All of them are linear. So overall, we have a linear programming model equivalent to this nonlinear programming model. So for the L infinity metric, or the maximum difference, if we want to minimize the maximum difference between the delivered dose and the target dose, this problem again can be reformulated by introducing a new variable. Now we only need one new variable, z, such that z is greater than or equal to the max here. But since z is greater than or equal to the max, then z should be greater than or equal to each absolute value over each pixel. So that can be reformulated as z is greater than the inside of the absolute value and greater than or equal to negative z for every pixel. Again, this is a linear programming model. So both problems can be reformulated as a linear programming problem, and both linear programming problems are always feasible. And the result is a radiation treatment plan that is close as possible to the target plan. Okay, let's summarize for this lesson. We created first an idealistic LP model for radiation therapy planning problem. It's idealistic because it may not be always feasible due to the complicated shape of tumor and critical area. And then we created a realistic nonlinear programming model using convex piecewise linear functions, either as the sum of the absolute value function or as maximum of absolute value function. Both are convex piecewise linear function. And then we reformulate these nonlinear optimization problem using convex piecewise linear function as a linear program. That's our lesson for radiation therapy planning using convex piecewise linear function. Thank you.